All right, so we're looking at L-Trominoes today. So an L-Tromino is a shape formed by joining three unit squares along their edges to form an L shape. So you've got these sorts of different rotations of that, what's called an L-Tromino or Tromino. And these are the questions we're going to consider. So can an 8x8 board be covered with 21 Trominoes with one square left over? Where could that missing square be? Same question for 16 by 16. Same questions for 10 by 10. And then these next two are grayed out because we're going to talk about these in another video, because I've been in this world for a bit and it actually gets quite tricky when we think about a 50 by 50 and then a general N by N. So these are the questions we're going to explore today. If you are finding these videos useful, please consider subscribing. I've set up a Patreon. I don't really know what that is, but apparently you can donate like $3 a month or something. I'm sure I'll find a way to repay you in the future. I'll give you some shout outs now. But if at some point in the future people actually watch my videos, then maybe I will be able to reward your dedication early on. Anyway, so think about that for me if you don't mind. Let's have a look at what we're doing here. So if we look at an 8x8 board, we can say the following. Let me just let this play for a bit so you can get a sense of what's going on here. It's not going to work because I need to go back and explain it. So an 8x8 board has 64 squares, just like a chessboard. Each L-Tromino covers 3 squares. So we can think about sort of divisibility by 3. 64 is just 3 times 21 plus 1. So 21 Trominoes, sorts out the area with exactly one square left uncovered, just in terms of area. But we need to think about whether we can actually tile it. So we need to think about maybe a strategy. And one strategy that might come to mind is I encourage you to get out a chessboard and think about how you could get these little Trominoes to fit on there, because I've certainly been doing a lot of that in the past couple of weeks. But one thing you could probably maybe come up with is sort of using what's called a divide and conquer type method. So you've got your 8x8, but each 8x8 board is made up of 4 quadrants of 4x4s. And in fact, those 4x4s are made up of 2x2s. So we can see that there's a sort of recursion going on here. We're sort of just getting a bit smaller. So we've got an 8x8, then we've got, quadrant 1 is up here, it's a 4x4. And then, this is a quadrant within a quadrant. We think about the base case. So a base case is a 2x2 minus 1 square, which is an L-Tromino. So we've got our little 2x2 here, and minus one of the squares is an L-Tromino. So in this diagram here, each color is one L-Tromino. And, just by that logic, hopefully you can see by a theory called Golomb's theory, any 2 to the k by 2 to the k board with one square removed can be tiled by L-Trominoes. So I think that's interesting. 2 to the k meaning basically a power of 2 board. So an 8 is 2 cubed. So 2 cubed by 2 cubed board can be tiled, as we can see here. Here's a valid tiling. And just by using this logic, right, like if we go back a bit, we can put in a central Tromino here. The uncovered square will be in this one, because this hasn't been given that extra square to be filled in. So our uncovered square is going to be in the quadrant that hasn't got our L-Tromino kind of joining the quadrants together. And when you see that when you tile it, here's an example of a valid tiling. Our uncovered square is here. Any 2 to the k board can be tiled. Now, you might be wondering, where can that uncovered square be? That was just one example. But we can actually realize that the uncovered square can be at any point. So at each recursive step, we place the central Tromino to cover the corner of the 3 quadrants that do not contain the missing square. It works for any starting position. All right, so if we just sort of zoom into one of the quadrants, we could have arranged it such that if we put the central Tromino in this within our sort of 4x4 now, then we can see where the central Tromino isn't, the sort of mini quadrant in here, we can have our missing corner there. So we can have a missing corner. Similarly, here's a valid tiling showing that we can have a missing edge. And here's another valid tiling showing that we can have a missing interior. So each color is obviously a Tromino, and the white one is uncovered. You've worked that out. Anyway, so the recursive argument works for any of the 64 squares. So all 64 positions are valid. So I really want to make that clear. So you're sort of imagining these quadrants inside a larger 64 square, but each of these, well, you know, if this was in the bottom left quadrant, for example, then you could have the corner missing, you could have any of the edges missing, and you can have the interior missing. So any of the 64 squares could be missing, missing a square. And yeah, that's basically where the uncovered square can be. I think that's, you know, reasonably interesting. What about the 16 by 16 board? Well, 16 is a power of 2, so we're safe using that Golomb's theory thing that we spoke about. So 85 L-Trominoes will be needed to cover the 255 squares, plus exactly 1 uncovered. And again, it's just bigger this time, right? Instead of being 8 by 8, it's 16 by 16, but we're using that same strategy of sort of placing a central L-Tromino in sort of our quadrant. So it can be any of the 256 squares in a 16 by 16 board for the same reason, because it sort of follows this pattern. The 16 by 16 board is just, can be broken up into 8 by 8s and 4 by 4s and 2 by 2s. So yeah, I think that's pretty interesting. Here's one that's a little bit more interesting. So if we have a 10 by 10 chessboard, 10 is not a power of 2. So we can still think about the count just in terms of areas. So we've got 100 equals 3 times 33 plus 1. So we're going to need 33 L-Trominoes with 1 left over. But 10 is not a power of 2, so we can't use that sort of recursive pattern. So we need a bit of a different strategy here. The key is to sort of embed a power of 2 within your 10 by 10 board. So if we've got our 8 by 8 board, then we can tile that 8 by 8 board with 1 square missing. And the 2 remaining, we'll sort of have 2 remaining rectangles on the outside. So here we go. This, I think, explains it. You can see at the top here, we've got a 2 by 10 and then sort of a 2 by 8 here. So that's what's left over. And if we look at a valid tiling here, I think it's probably easiest just to show that the missing square can be anywhere in the 8 by 8, because that's what we just spoke about. But this can be tiled perfectly because it's got 36 squares and it can be tiled nicely. Yeah, here I'll just show you. So there we go. We can have our 8 by 8 with any of these squares could be missing. It just happens to be missing here. And then we can tile the 36 squares in the border like this. We'll talk in the next video in more detail about why those 2 strips can definitely be tiled with L-Trominoes, but rest assured that it can be done. Basically, if you have a rectangle with side dimensions that are a multiple of 2 and 3, such as in this case, because you've got a 2 by 8 and a 2 by 10. Strike that. Don't take that super seriously. I might have got that wrong. So anyway, just rest assured that the 36 squares can be done with the L-Trominoes. And sort of just the other thing to point out is this is the missing square here. It's in the interior, but we know that that missing square can be anywhere. The missing square can be on the side, can be in the corner, can be anywhere. So then based on rotations of that, any of those squares in the 10 by 10 could be missing. Yeah, we'll talk more in the next video about a 50 by 50 board, and it just jumps up a whole nother level in terms of difficulty. But stay tuned for that. If you found that interesting and sort of thought-provoking, give us a thumbs up. Let us know what you think. This is just what I think about it. Yeah, there's a beautiful world of maths out there to explore. So yeah, talk to you soon. Oh, I forgot that this is here. Answer: the uncovered square can be any of the 100 squares. Yep, we spoke about that. Good stuff. All right, I'll see you soon.